For this lesson, we're going to be working on simplifying radicals, so we'll need to understand perfect powers, simplify them using the product rule and quotient rule. So we'll go through those things to simplify radicals. Okay, so for your bell ringer, you had these 5 questions. If you haven't got them done yet, please pause the video or continue and get them done. Okay, so for the first few, we're just rewriting these in radical form. So remember, we have this exponent of 1/5. Remember, the bottom number is the index, and the top number is the power. So it's power over index. So we want a 5th root of 6a plus 5b inside the radical. And if you want that in parentheses, you can do that. You don't necessarily need to. Okay, so with that, that means this one is going to be 5th root of x to the 3rd. And then another reminder with this is you can put the 3rd power on the inside, or we can have it like this on the outside, whichever one you prefer. Sometimes this way helps you get it simplified, sometimes it doesn't. Okay? And then we're doing this one, 4th root of that. So 4th root, 3n to the 4th, j, and that's raised to the 3rd power. And we probably want to simplify that one down. So 4th root of 3 to the 3rd power is 27, n to the 12th, j to the 3rd. Okay? And then we will be working on simplifying stuff like that today. Okay? Or we'll be working on simplifying this today. I'll show you how it looks just in case. So 27 of the cube, so that one can't do anything. And then we look for groups of 4 out of the n. So we can take 3 groups of 4. That gives us n to the 3rd outside. And then we can't do anything with that j to the 3rd. So on the inside, we'll have 27 j to the 3rd. And that's what we're going to be doing today. Okay, and then this one, we're just working the other way. So we're rewriting this in exponential form. So it's power over index. So, oops, let's put that in parentheses. I guess we don't really need parentheses, but it'd be 14 over 3. Power over index. And then the next one, same thing. So this one we should have parentheses. Okay, and this will be raised to the 1/3 power. Okay, because that is a power over index, or excuse me, power is the 1, index is the 3, and we could distribute this exponent if we wanted to, but I think it looks a little bit uglier if we do that. So it'd be 3 to the 1/3, x to the 5/3, okay, and I think that this is way messier than that, so I prefer this. I'm going to get rid of that. Okay, so there's your little bit of warm-up for today's lesson. So, understanding perfect powers, we're going to look at these. So if we have the square root of 36, that's just a 6. And remember, some of the lessons we did plus or minus, depending on if we were just straight up simplifying these or if we were simplifying a group of things in there. All right? So square root 64 plus or minus 8. 5th root 32. So remember, it's a 5th root, so whatever the odd indexes are, if those are an odd index, that keeps the sign. So if 32 is positive, so we're going to have a positive 2. So we don't need to write the plus or minus with that one like we did with the square roots. Same thing with the cube roots. So this would be a 3 here, and it retains the sign. Square root 81 plus or minus 9. And 4th root of 16 plus or minus 2. Okay? So remember with this one and this one, the bigger indexes, you ask yourself, what time does self that many times get you the number on the inside? And then generally, if it's a smaller number, like 32 or 16, you would start with 2 and start multiplying it up until you get there. Or if it's like an odd number, you'd probably go with a 3. So like if I had 4th root of 81, that's a little bit bigger, but it's an odd, so I'd probably go with a 3 and see if I get there. Okay? So if we have several things being multiplied underneath the radical, such as this right here, we can split it to have each of those variables or each of those numbers. That's called the product rule. Okay, so you want to try to split things. We also have the quotient rule coming up here, but the product rule is when you try to split things being multiplied to simplify it. Okay, and there are some instructions if you would like to read those. I'll just start showing you how to do it. Okay, so you should remember these from previous classes. You've done it in geometry and you've also done it in Algebra 1. But what you want to start doing, so 28 is not a perfect square, right? Because if you just start multiplying by 2, by 3, by 4, you won't hit 28. So what you do is you start breaking this down, okay? So I like to do it where we break it down by the smallest numbers possible. So it's easy to divide by 2, so I can do this in my head. Okay, so 28 divided by 2 is 14, and then 14 turns into a 2 and a 7. So since this is a square root, an index of 2, we usually don't write the index of 2, but that's what's implied. You're looking for pairs, okay? So I have a pair of 2's. Whenever I have a pair for a square root, I can bring those out, and then I leave that underneath the radical. So square root of 28 would turn into 2 square root 7 when I simplify it down. Okay? That, in my opinion, is the easiest way to do these. There is another way here that I'm going to show you, but I'm going to do the way normally where I just break it down into the smallest factors possible, and then look for pairs for square roots, triplets for cube roots, and groups of 4 for fourth roots. Okay? The other way is you break it down into perfect squares, and that would be technically using the product rule perfectly. So in that way, I have to memorize what perfect squares I'm taking out of this. So I will try to take out the largest perfect squares I can. So in this case, 4 would be the largest perfect square, and I would have a 7 left. And those are technically square roots, and that's using the product rule. So if I break these down, I know that square root of 4 is a 2. And I can't do anything with square root 7, so that is left as square root 7. Okay? That's the way you do it if you're looking for perfect squares. And I'll show you that again with 32 here. So I think of the biggest perfect number, perfect root that goes into 32, and I break this down. So that'd be a 16 times a 2. Okay? We know square root 16 is a 4, and then square root 2 doesn't go down any further, so it's just square root 2. So that is what you have for that one. Okay? Let me show you, let me do the rest of these by breaking them down as far as I can, because that is, you can kind of apply that for any scenario, and you don't have to memorize perfect squares and perfect cubes. Okay? So 60, we're breaking down 6 and 10. Okay, that's probably the easiest combination to break that down into. And then 6 is a 2 and a 3, and 10 is a 2 and a 5. And then you're looking for pairs. So I have a pair of 2's. Okay? The 3 and the 5 are not a pair of anything, so those go back underneath there. Okay, so pair of 2's gets me a 2 in front of the radical. And then since I have a 3 and a 5 going back into that, I have to multiply those back. All right, because we're using the product rule here. All right, we're just breaking down factors or numbers to see what they multiplied to get. All right, so 3 times 5 is 15. So this one is 2 root 15. Okay? So if you wanted to try these next few on your own and then come back for the answers, go ahead and pause the video. Otherwise, we'll keep going. Okay, so D is 5 and 10. And 10 is 2 and 5. And then we look for pairs again. So I have a pair of 5's. So those will get me a regular 5 in front of the radical with a 2 back underneath. Okay, so 72 might be a little bit bigger because it's an even number and it's kind of bigger. So let's start breaking it down. So 2 and 36. And here, if you recognize that 36 is a perfect square, you could do that one right away because these are square roots. But we'll just keep breaking it down. Okay, so 36 is 6 and 6. And then 6 and 6, that's 2 and 3 and 2 and 3. And then you look for pairs. So here we got a pair of 2's and then a pair of 3's. So that means we're bringing a 2 and a 3 in front of the radical. And when you do that, you multiply those because, again, we're using the product rule. Okay, so the 2's give me this 2. The 3's give me this 3, and those got to multiply, so it's 6 root 2. Okay? So remember, whenever I bring something out of a radical, if I'm bringing multiple things out of the radical, I multiply them in front, as we did here. If I'm leaving multiple things under the radical, like this one, those multiply when they go back under, okay? All right, square root 125, break it down. So 5 and 25, and then the 25 breaks down to a couple of 5s. So there's a pair of 5s. That comes out, and we leave 1 underneath, okay? And there we have it. So down here, these are the other ones I was talking about. We have cube roots, okay? They work exactly the same way. You can look for perfect cubes, or you can do what I did up here and break them down. I think if you just keep breaking stuff down, that's the easiest way to do radicals, okay? So 16 breaks down into a 2 and an 8, and an 8 is a 2 and a 4, and a 4 is a 2 and a 2. Okay, so when you're breaking these down, make sure if you have a longer factor tree or a taller one, that you keep track of where your bottom factors are, the smallest numbers. Okay, now we're looking for 3 of a number. So 1, 2, 3 2s. Since we have 3 of those all come out in front as a regular 2. That one goes back. And you have to remember, put the index back with it, okay? Because it's not a square root, it's a cube root. The indexes never change. Okay, let's break 54 down. So 2 and 27 is 3 and 9 is 3 and 3. So we have a triplet of 3s. Those come out, and then we have the 2 that goes back underneath there. All right, and then one more left. We got 4th root of 32. So now we're looking for 4 of a number because it's a 4th root. Okay, so break that down. 2, 16, 2 and 8. And sometimes I like to be a little lazy with the 8 because I know the 8 is 2, 2, 2. It's 3 2s. Okay, and then we're looking for a 4th root. So 1, 2, 3, 4 2s. Those come out. And I leave the other one back in there. Okay, so depending on what the root is, that's how many you're looking for in your bottom of your factor tree. If you have enough of them, bring them out and leave anything that's left underneath your tree back in the radical. Okay? So now we're doing the same thing, but with variables. Okay? So square root, you're looking for 2 of something. Cube root, you're looking for 3 of something. 5th root, we're looking for 5 of something. All right? So here is one way you can do this. So I know that x to the 4th is 4 x's, right? And I have a square root, so I'm looking for pairs of 2. So I have 2 pairs of 2. So that's just an x squared. And if I use everything underneath the radical, that means that was a perfect square and there is no more radical left. Okay? So for b, this is the way that I've shown you before. You take the power and divide it by the index, just like the stuff we did in the previous lesson where you do rational or radical exponents or fractional exponents. So 12 divided by 3, that's 4. So that's one is x to the 4th. Okay? And same thing here. 40 divided by 5, that's 8. So this is x to the 8th. And since these all worked out to perfect variables or perfect numbers, they're all perfect squares. Okay? Or perfect roots. So for this one, though, I have a square root. And if I divide 9 by 2, I get 4.5. Okay? I can't leave 4.5 as an exponent when I'm simplifying radicals. That doesn't work. Okay? So what you got to do is you're kind of dividing 9 by 2, and then you leave the remainders underneath there. All right? So I know that x to the 8th divides nicely by 2. So that would be 4 out front. And that means there's one of those left. So this is the way that would simplify. Okay? And let me show you another way to do this. Just like what we did up here. All right, you're going to write out 9 x's. And you're circling groups of 2. So there's a group of 2, there's a group of 2, there's a group of 2, there's a group of 2. 4 groups of 2 would be x to the 4th. That one goes back underneath there. Okay? That way is going to take you quite a bit more time, especially when you have something like this. But if you forget, that's what we're doing. Okay? So we're going to do the division method here with our exponents. So what number, if I divide 23 by 5, what's my remainder? How many do I have left? Well, I know that this is x to the 20th and then x to the 3rd. Okay, and 5 goes into 20 nicely, so that would be x to the 4th. And then I have x to the 3rd stuck underneath there. So 5th root of x to the 3rd goes back as the radical. Okay, so you divide your exponents by the index, and then your remainder, okay, whatever's left that doesn't come out nicely, that goes back underneath the radical. All right, so y to the 33. How many nice groups of 4 can we get out of 33? Well, I know that 4 goes into 32, right? So 4 goes into 32. Let's write this like we had before. So 4th root of y to the 32, and then there's a y left. So 4th root of y to the 32, that's y to the 8th. And then we have 4th root of y left. Okay? So divide nicely out of the variable, and whatever you have left goes back underneath. So here's a couple where you have two different variables, but we're doing it the same way. We're looking at the first variable, and then we're looking at the second variable. We just kind of go from left to right, looking for things that divide nicely. And again, this is a square root. If you forget, put the 2 in there. Okay? So I can divide this nicely by the 2, so that's x to the 6 on the outside. That one does not divide nicely, so we can look and see how many we can take out and how many we have to leave under. So I know that 2 goes into 16, so that'll be a y left here, and then we have y to the 8th, because 16 divided by 2 is 8. All right? So that is that one. And again, if you need that little reminder, y to the 16th, y to the 1st, and then you ask yourself, how many nice groups of 2 can I get out of that 16? Okay? How many groups of 4 can I get out of the 6? Well, I can only get one nice group of 4, so that means there's an x out in front, and I'm going to write this radical here because I know there's stuff going back underneath. All right, so if I took 4 of those, there's 2 left. How many nice groups of 4 can I get from that? Well, I can take 20 of those to get 5 groups, so that's y to the 5th. And I said I'm taking 20 of those, so 3 are left. Okay? So these ones are a little bit difficult because I'm doing that step several times in once. But again, divide the exponent by the index. The remainder goes back underneath. All right? So in these, we're doing kind of everything together. Okay? So we have to break down our number, and then we break down our variables. All right, so let's factor tree the 32. And remember the 8, I like to do 2, 2, 2. And we're looking for groups of 2 because this is a square root. The index isn't written, but it's implied. Okay? So a group of 2 here, a group of 2 here. And since we're taking both of those out, that turns into a 4 in the front. And again, I'm going to write my radical because I know that things are going to go back underneath. That 2 goes back underneath. So I do the numbers first. And then I'm going variable by variable from left to right. Okay? And it looks like those are going to divide nicely. So I look at how many groups of 2 I can get from the 8. So I would turn that into x to the 4th because I can get 4 nice groups. And how many groups of 2 can I get from the 6? That's going to be 3 nice groups. And I have that. Okay? So factor tree the number and then divide the variables. All right? So pause the video, work through these 3, and then come back and then see how you did. Okay? So this one, I'm breaking down 8 and 10. 8 is 2, 2, 2. 10 is 2 and 5. This is a square root, so we're looking for groups of 2 right there and right there. So again, I'm taking 2 2's out, which gives me a 4 in front. All right, that 5 is going back. So 5 in there. And I just write this radical here just because I know there's things going back underneath there. It doesn't matter how long it is, we can fix it in the end. Okay? How many nice groups of 2 can we get from that? Okay, well, we can get 2 groups of 2. That would be x squared, because we can take 4 of those, and that'll give us 2 groups of 2. That means 1's got to go back underneath there, right? If I look at this, write out 5 x's, circle groups of 2. So we got an x squared and an x. All right? Y to the 12th, that divides nicely, so that's y to the 6th. And then z to the third, that doesn't divide nicely. We can take one group, and then we got to put 1 underneath. Okay? So this is our answer in the end. All right, let's try C and D here. So 54, we're breaking down. 2, 27. 27 is 3 and 9. 9 is 3 and 3. Now we're doing a cube root. Okay, so we're looking for groups of 3, which we got right there. So that brings a 3 out. I'll write my cube root back. 2 goes inside there. And now we're dividing these by 3. So how many nice groups of 3 can we get out of there? Okay? If you can't do that in your head, then start counting by 3s until you get beyond 17. Okay? I know that I can take 15 of those, right? If I did 15, I'd have 2 left. So 15 divides nicely by 3, so we have x to the 5th, x squared. And now we're doing the same thing with this. So we could do a 24, and we'll have 1 left. 24 divides nicely by 3. That gets us an 8. And we said we got that 1 left. And then we're doing the same thing with z. So z to the 6 divides nicely by 3. That just gets us z squared. All right, and that is that one. And one more of these before we get to the quotient rule. All right, so 62, break it down. 2, 31, and 31 is prime. Okay, so if we look at these, we can't really do anything with the 62. So let's get rid of that and just leave it. So 62 back underneath there. And then we're dividing exponents by 5 and see what we got left. So x to the 10th divides nicely by 5, which is 2 groups of 5. So that's x squared, and x squared back underneath. Divide this by 5, and that works out nice. We get y to the 4th. Divide this by 5, we get z to the 3rd. And that is all for that one. Wasn't too bad. Okay? So that is using the product rule to simplify radicals. Now we'll look at the quotient rule here. So quotient rule is the same kind of idea. It's just division. Okay? If I have a radical with a fraction in it, I split that to a radical on the top and a radical on the bottom. I'm essentially distributing the radical, but I don't want to say that for sure. That's kind of loosely distributing the radical. Okay? So let's look at these. So we could start factor treeing these, but you want to think about the product rule here before you start factor treeing. So can I put these together under the same radical and see if those divide? Okay? Because really, square root of 3, we cannot have radicals on the bottom that do not simplify nicely. Okay? So 75 over 3 does work out nice to 25. And then, hey, 25 is a perfect square. So that's 5. Okay? So same thing on B and C. You want to try to put these together and then simplify them in the end. Okay? So we got 24x over 3x. And we've simplified stuff like this before. The x is going to cancel out, and then 24 divided by 3, that's an 8. Okay? And cube root of 8, another perfect radical. Cube root of 8 is a 2. Okay? Same idea with C. So put them under the same radical. X to the 4th, y to the 7th on top, x on the bottom, y to the negative 5th. All right? And now with these, remember you're thinking, to simplify, I subtract from the bigger variable. Okay, so the x's are going to go up and subtract from that one. So we'd have x to the 3rd. Okay, let's give ourselves a little bit of room here. We have this underneath a cube root still, so I have x to the 3rd. And then if I subtract that from there, it's going to change it to a positive, bounce this up. It'd be plus 5. 7 plus 5 is y to the 12th. And now we're using that cube root. So how many groups of 3 can we get from the x? 1. Works out nicely. How many groups of 3 can you get from the 12? 4. Also works out nice. Okay? So put these together under the same radical if they match, which most of the time they will. All right? The other version of this is to split them. Okay? So I have a 121 on top, a 25 on the bottom. I cannot divide 121 and 25, so I should try to split it like that, and then just do radicals. So square root of 121, that's 11. Square root of 25, that's a 5. So those are both perfect squares. Okay? Now for this one, does that help us out if we split it? So let's look at this. If I split this to 4th root of 3, 4th root of 48, 48 is not going to be a perfect 4th root. So I would see that if I started factor treeing. So I don't want to split this. I want to leave that and just divide those two. So I can divide those two, and it gets me a 16 on the bottom, right? So divide by 3, just reduce it like a normal fraction. 4th root of 1 over 16. Now, I can use my power, or my quotient rule, to split those. Take the 4th root of the top, take the 4th root of the bottom. Okay, if we want to write that, we don't really need to, but I'll do it just so we can see it. 4th root of 1 is 1, 4th root of 16 is a 2. So that turns into a half. Okay, so really you have to kind of decide what you want to do with the quotient rule and product rule. Do you want to split it, or do you want to leave it and divide it first? I would say if you can divide it first, that's what I would do, and then split it later. Okay? So like this one. Can I divide the top and bottom? Yeah, 27 divided by 3, well, that's a 9. And then I subtract the x's from the larger variable, so that'd be x to the 4th, and these are in a square root. Okay? So those are perfect squares. Square root of 9 is a 3. Square root of x to the 4th, well, we just divide the exponent by 2, x squared. Okay, couple more down here, a few more. So same idea here. If you wanted to pause these, try them, and come back for the answer, that's fine. Otherwise, we'll keep rolling here. So variables, I subtract from the larger one, so that means this is going to move up, subtract from that, but it'll change to a positive, right? Because we flip those signs. So we'll have x to the 8, y to the 20th, all under a cube root. So then we divide our exponents by 3. They don't divide nicely. So now we're thinking, how many groups can I get out? So how many groups of 3 can I get from the x's? Well, 2. And then whatever's left, so that would be 2 of them left, right? Because it'd be x to the 6 times x squared. So these are my nice groups of 3. X squared goes back underneath there. How many groups of 3 can I get from 20? Well, I know that 3 goes into 18 6 times, right? So it'd be y to the 6. And then we said 18, so that means there's 2 left. So that's the simplified version of that one. Okay? Now this one, we kind of have a few things that we can do. We try to divide first. So 8 and 27 does not divide. The x's do, the y's do. All right? So let's do that first. So 8 is on top. We're taking one of the x's out. So I have x to the 3rd, taking one of those. Okay, and then 27 is on the bottom, and we're taking one of the y's out, so y to the 9th on the bottom. And this is in a cube root. So now we want to split it to top and bottom. Cube root 8x to the 3rd over cube root 27y to the 9th. And those are perfect cubes. Okay, 8 turns into a 2, so the top is just going to be a 2x. Okay, because we get our 3 groups of x's. And the bottom will be a 3y to the 3rd. We got 9 y's. Okay? So for f, same thing. Can we simplify first? Well, 3 goes into 18. We just had that on the last one. That'd be a 6 on top. Take the x's out, so that's going to be taking one from the bottom. That's where the bigger x is, so x to the 8th. And then taking one of the y's out, y to the 4th. And this is 4th root. Okay? So I cannot do anything with that 6, so that's going to have to stay there. So let's break this down still. 4th root of 6y to the 4th. 4th root of x to the 8th. So we split it, break it down. So the top, we can only take out the y's. So it'll be y 4th root of 6. And on the bottom, how many groups of 4 can we get from x to the 8th? We can have 2 groups of 4, which is x squared. And that's what we have when we simplify. Okay? So if you want a little bit more practice, we'll try 7a and b. If you're good, then you can skip to the end of the video here. All right? So this one, same as the last one, we break the m's and n's down. I can't divide 27 and 64. I don't want to because I recognize those are perfect cubes. So I would have cube root 27 on top, 64 on the bottom. M's, we take one away, so that's m to the 6. N, we're taking 2 of those away from the bottom, n to the 15th. Okay, split top and bottom, or cube root top and bottom. We'll have 3m squared, because those are perfect cubes. And on the bottom, we'll have 4 n to the 5th. Okay, because how many groups of 3 can we get from n to the 15? It's 5. All right, so these two right here, I got a 10 and an 81. I can't do anything with those. I'll simplify the x's. So 10 stays on top, 81 stays on the bottom. X's, so the bigger one's up here, so I'm moving this up. It'll add 8, so that's x to the 12th, y. And then we have this in a 4th root. So then we'll look to split the root for the top and the bottom. Okay, 4th root of 10, you can't do anything with that, so leave it. 4th root of x to the 12th. We can take out 3 groups. And we can't do anything with the y. So the top is going to look a little interesting. We have the 10 and the y left. And then the bottom, 4th root of 81 is a 3. Okay, that's a perfect 4th root. And there we have it. All right. So that concludes the lesson. We now know how to simplify perfect radicals with exponents. We can change them to a fractional exponent, and we can simplify them by grouping them using the quotient rule and product rule. Okay? So if you have any other questions, let me know. Otherwise, thank you for watching. Please leave me a like if you enjoyed the video and you understand what's going on. Have a great rest of your day.